Today, we'll have a quick review of chapters 5, 6, and 7. Then we'll have the chapter 7 quiz. You get one sheet of notes, double-sided. You'll need a calculator. The final test on chapters 5, 6, and 7 is on Wednesday. That's all that's scheduled for Wednesday. Okay?
You already.
Okay. Again, you get one sheet of notes, double-sided. You'll need a calculator. And the lab today is for makeups. If you need to make up any labs. And if you have to make up labs or other things and you don't manage to get it done today, I am available like from 10 to 1 all the other days of the week. You can come in early on Wednesday, you can come in on Tuesday, things like that. So, chapter 5, which was on heat. So to start with, we talked about temperature, which is a measure of the average kinetic energy of a substance. It's measured in degrees Celsius, Kelvin, or Fahrenheit. Here are the conversions. To go from Kelvin to Celsius, you add 273. To go from Celsius to Kelvin, you add 273. To go from Kelvin to Celsius, you subtract 273. 0 degrees Celsius is 273 Kelvin. Name?
Hey.
Morgan?
No.
Sorry. We're just right next to it. To go from Celsius to Fahrenheit, you multiply by 1.8 and add 32. To go from Fahrenheit to Celsius, you subtract 32 and then divide by 1.8. As usual, you can write these down in your notes for the test. So, for example, what is 30 degrees Celsius in Fahrenheit? Temperature in Fahrenheit is 1.8 times temperature in Celsius plus 32. So 1.8 times temperature in Celsius plus 32. 1.8 times 30 degrees Celsius plus 32 is 54 plus 32. That is 86 degrees Fahrenheit. Now, heat is energy that's transferred from one object to another as a result of a temperature difference. It's energy in transit because of that temperature difference. Heat is energy, unit is joules. But because for historical reasons, we also use the calorie, which is the heat required to warm 1 gram of water by 1 degree Celsius at normal atmospheric pressure. 1 calorie is 4.186 joules. A kilocalorie is the heat necessary to raise 1 kilogram of water by 1 degree Celsius. 1 food calorie for food packaging is 1,000 kilocalories. It's 1,000 calories or 1 kilocalorie, and 1 food calorie is 4.186 joules. So how many joules are in a 300 food calorie chicken sandwich? 1 food calorie is 1,000 calories. 1 calorie is 4.186 joules. So 300 food calories is 300,000 calories. So 300,000 calories times 4.186 joules per calorie gives you 1,255,800 joules. But this is 3 significant figures, so you round it to 1,260,000 joules, or 1.26 times 10 to the 6 joules. You could also take that 1 food calorie is 4,186 joules and do this by multiplying 300 by 4,186. So, to change the temperature of something requires energy. That energy, that heat, is called the specific heat. The heat capacity, the specific heat capacity, which is written as a C, is something that tells you how hard it is to change the temperature of something. Name? So the amount of heat required for a change in temperature is the mass of the substance times the specific heat capacity of the substance times the change in temperature. And this applies to a substance that is not undergoing a phase change. If something is melting or boiling, you have to use latent heat instead. So how much heat does it take to warm 3 kilograms of water with a specific heat capacity of 1 kilocalorie per kilogram degree Celsius from 12 degrees Celsius up to 32 degrees Celsius? It's also important on these to pay attention to units. The heat is mass times heat capacity times change in temperature. So the mass is 3 kilograms. The heat capacity is 1 kilocalorie per kilogram degree Celsius. The change in temperature is 32 degrees Celsius minus 12 degrees Celsius, 20 degrees Celsius. So 3 times 1 times 20 gives you 60 kilocalories. Latent heat. Latent heat is the energy required to change the phase of something. You turn something from a liquid into a gas or a solid into a liquid, for example. The heat required to melt something is called the latent heat of fusion. You can calculate if there's a latent heat of fusion, LF. You multiply the mass of the substance times the latent heat of fusion to find the heat required to melt something. To bring something to a boil, and to boil it and turn it into a gas from a liquid, that is the latent heat of vaporization. So the heat required is mass times latent heat of vaporization. Those are the only latent heats we're going to worry about in this course. There are, of course, other ones or other transitions. So, for example, when dry ice goes from solid directly to gas, that's the latent heat of sublimation, but we're not going to worry about it. So how much heat does it take to melt 2.5 kilograms of ice at its melting point? So latent heat is applied at the melting point or the boiling point. Temperature is not changing. You're just putting heat in to change the phase. So 2.5 kilograms of ice at its melting point of 0 degrees Celsius. The latent heat of fusion is 80 kilocalories per kilogram. So we'll multiply mass by latent heat of fusion. 2.5 kilograms times 80 kilocalories per kilogram gives us 200 kilocalories. And then if you have a confined gas, an ideal gas, it follows the ideal gas law. Pressure is directly proportional to the number of molecules and the temperature in Kelvin, and inversely proportional to the volume. The pressure is proportional to N times T over volume. So P2 over P1 equals V1 over V2 times T2 over T1. And then it would also be times N2 over N1. But N will be constant in all the problems I give you on the test and on the homework. So we're not going to worry about changing N. And the full form of the ideal gas law is PV equals nRT, or PV equals NK Boltzmann T, depending on whether you're counting individual molecules or moles of molecules. This one is the one that's used more often, where R is this constant, gas constant. It turns out that relationship, that ratio of pressure times volume over number of molecules times temperature, is constant for all gases, basically. Name? Your name? So if I take a sealed tells you N is constant. Rigid tells you volume is constant. Container of helium gas at 77 Kelvin and a pressure of 1 times 10 to the 5th pascals, and warm it up to 308 Kelvin. What will the pressure at be? So sealed tells me N is fixed. Rigid tells me volume is constant. P2 over P1 equals V1 over V2 times T2 over T1. But volume is constant, so that term is going to go away. V1 over V2 is a constant because volume doesn't change. So P2 over P1 equals T2 over T1. So P2 equals P1 times T2 over T1. So 1 times 10 to the 5th pascals times 308 Kelvin over 77 Kelvin, which is 4 times 10 to the 5th pascals. So because I quadrupled the temperature, I quadruple the pressure. And in general, most matters, solids, liquids, and gases will expand with an increase in temperature and contract with a decrease in temperature. The big exception to this rule is water, which below about 4 degrees Celsius expands, and then as it turns into a solid, it significantly expands. Ice floats. Heat transfer occurs via 3 methods. There's conduction, which is heat being transferred just through contact or flowing through a non-moving substance. Convection is heat being carried by a moving substance. So conduction is, how heat travels through a pan or up this rod. Convection is heat being carried by the rising warm air here, or air being blown around in your car or in, say, an air fryer. And then lastly, radiation is heat being transferred by electromagnetic radiation. So conduction is the transfer of heat by molecular collisions. How well a substance conducts depends on its molecular bonding. So metals tend to conduct pretty well. And thermal conductivity is a measure of a substance's ability to conduct. Liquids and gases are generally poor thermal conductors because their molecules are far apart, particularly gases. Metals are generally good thermal conductors because their molecules are close together and can transfer the jiggles quite easily. Convection is the transfer of heat by the movement of a substance or mass from one position to another. Most homes are heated by convection, the movement of heated air. Radiation is the process of transferring energy by means of electromagnetic waves, and they can carry energy even through a vacuum. In general, dark objects absorb radiation well, and light-colored objects do not absorb radiation well, they reflect it. Thermodynamics deals with the dynamics of heat and the conversion of heat to work, things like car engines, refrigerators, etc. The first law of thermodynamics is conservation of energy. The heat added to a closed system goes into the internal energy of the system and or doing work. So heat is change in internal energy plus work done by the system. Second law of thermodynamics is that it's impossible for heat to flow spontaneously from a colder body to a hotter body. And that means no heat engine operating in a cycle can convert all thermal energy into work. 100% thermal efficiency is impossible. You will have heat spontaneously move from a hot place to a cold place, but not from a cold place to a hot place. To move heat from a cold place to a hot place, you have to force it. You have to pump it. And so third law of thermodynamics is that it's impossible to obtain a temperature of absolute zero. Absolute zero is the lower limit of temperature. So you can't win, you can't break even, and you can't get out of the game. This is a heat engine. A heat engine takes heat from a high temperature reservoir, moves it to a low temperature reservoir, and turns some of it into work, but not all of it. A heat pump takes in work, pulls heat from a low temperature reservoir, and pumps it out to a high temperature reservoir. So it's easy to turn work just directly into heat. Heat pumps are better than that because they can pull some heat from a cold place and move it to a warm place. So we use heat pumps. We use heat pumps to efficiently warm places and also to cool things. Your refrigerator is a heat pump. So entropy indicates whether or not a process will take place naturally or spontaneously. It's associated with the second law. It's a measure of disorder of a system. Most natural processes lead to an increase in disorder. Entropy increases, and energy has to be expended to decrease in entropy. So for any natural process, the entropy of the universe goes up or stays the same. And since heat naturally flows from high to low, the entire universe will eventually cool down to a final common temperature, which will be quite low because the universe is expanding. And these are the important equations, how to convert Celsius to Kelvin, Kelvin to Celsius, Celsius to Fahrenheit, Fahrenheit to Celsius. There's specific heat, also with the change of temperature, latent heat, and the gas law. Now let's talk about waves from chapter 6. Wavelength is the distance of one complete wave. Amplitude is the maximum displacement of any part of the wave from its equilibrium position, and the energy transmitted by the wave is directly proportional to the amplitude squared. Frequency is the number of oscillations or cycles that occur during a given time, i.e. a second. The unit is hertz. Hertz are inverse cycles per second. Period is the time it takes for a wave to travel a distance of one wavelength. Because of this, frequency and period are inversely proportional. Frequency is 1 over period. Period is 1 over frequency. So the frequency of a wave with a period of 0.0001 seconds. Frequency is 1 over period. 1 over 0.0001 seconds is 10,000 hertz. So this is 10 to the minus 4. This is 10 to the 4. Since speed is distance over time, velocity ends up being frequency times wavelength. And so frequency is velocity over wavelength. The wavelength is velocity over frequency. So here's wave speed. Same frequency with different velocities. You get a higher wave velocity leads to a longer wavelength for the same frequency. Lower wave velocity leads to a shorter wavelength frequency. So what's the wavelength of a wave with frequency of 20 hertz and a speed of 40 meters per second? Well, speed is frequency times wavelength. So wavelength is speed over frequency. So 40 meters per second divided by 20 hertz gives you a wavelength of 2 meters. Electromagnetic waves consist of vibrating electric and magnetic fields that oscillate perpendicular to each other and the direction of wave propagation. Field energy radiates outwards at the speed of light. Speed of light of all electromagnetic waves, c, is 3 times 10 to the 8th meters per second. That's also a good approximation of the speed of light in air. The difference is beyond 3 significant figures. The human eye is only sensitive to a very narrow portion of the electromagnetic spectrum. We call this visible light. It's with wavelengths between 400 nanometers and 700. So 7.5 times 10 to the 14 hertz and 4.3 times 10 to the 14 hertz. So what's the frequency of a radio wave with a wavelength of 1.5 meters? So speed of light equals frequency times wavelength. Frequency is speed of light divided by wavelength. So 3 times 10 to the 8th meters per second divided by 1.5 meters gives you a frequency of 2 times 10 to the 8th hertz. Or 200 megahertz. Loudness and intensity. Loudness is a relative term. The intensity is a quantitative and is measured in the rate of energy transfer for a given area. It's measured in watts per square meter. The threshold of hearing is around 10 to the minus 12 watts per square meter. And an intensity of 1 watt per square meter is painful to the ear. And it decreases with distance from the source. So the intensity is proportional to 1 over the radius squared. So if you double the distance, you quarter the intensity. Sound intensity is measured on the decibel scale. A decibel is a tenth of a bell. And it's a unit of intensity named in honor of Alexander Graham Bell. And the decibel scale is not linear with respect to intensity. It's logarithmic scale. Therefore, when the sound intensity is doubled, the decibel is only increased by about 3 decibels. If you go up 10 decibels, that is the same as multiplying the sound intensity by a factor of 10 for every 10 decibels. So 10 decibels multiplied by 10, 20 decibels multiplied by 100. So how many times more intense is 32 decibel sound than a 12 decibel sound? Well, that's a 20 decibel difference. Plus 10 decibels is 10 times the intensity. 20 decibels is 10 squared times the intensity, or 100 times more intense. The Doppler effect is the apparent change in frequency that results from the relative motion of the source and the observer. As a moving sound source approaches the observer, the waves in front get bunched up, and the waves behind get spread out due to the movement of the sound source. So if something is moving towards you, you'll hear a higher pitch as the source approaches, and then a lower pitch if something is moving away from you. Same thing happens with light. Something comes towards you, you get shorter wavelength, blue light, bluer light. Something moves away from you, you get longer wavelength, redder light. But the scale of the shift is proportional to the speed of the movement compared to the speed of the wave. So it's much more obvious in sound than it is in light. But as you approach, waves get bunched up, higher frequency, behind waves are spread out, lower frequency. Standing waves occur as a stationary wave rising from the interference of waves traveling in opposite directions. On a rope or string, for example, waves travel back and forth. You get a standing wave where wavelength where the length of the string is a multiple of half the wavelength. So when these two waves meet, they constructively interfere with each other, forming combined and standing waveform. So here are some standing waves. Here's the longest wavelength, lowest frequency one. You can see the length of the string is half the wave. Here it's the whole wave. Here it's 1.5 waves, and so on. And the formula for the wavelength is 2 times the length of the string divided by n, where n is the number of antinodes, which are the big wobbly bits. Resonance is a wave effect that occurs when an object has a natural frequency that corresponds to an external frequency. So it results from a periodic driving force with a frequency equal to one of the natural frequencies. A slower one that you might be easier to understand is pushing a swing. You need to push the swing at the same point and it's swing each time, so you need to push with the same frequency to keep the swing going. But you can do that with like sound vibrations, and the dramatic cases of it, so you can get objects to vibrate enough to say tear themselves apart. So dramatic things can occur when resonance occurs, like you can shatter a wine glass with your voice. And there's been a couple examples of bridges tearing themselves apart or having really disturbing shaking because of resonance. So the important equations: frequency is 1/period. Speed is equal to wavelength times frequency, and the speed of light is 3 times 10 to the 8th meters per second. Let's talk about chapter 7. So the law of reflection is that the angle of reflection is equal to the angle of incidence. Very simple. The reflected and incident rays will also be in the same plane. So if a beam of laser light hits a flat plane mirror at 35 degrees to the normal, and that angle is measured to the normal, to the perpendicular, just because that's easier to define for curved surfaces. What angle does the light reflect? Well, the angle of incidence equals the angle of reflection, so the angle of reflection equals the 35-degree angle of incidence. So it will reflect at 35 degrees. Refraction is the bending of light waves caused by a speed change as light goes from one medium to another. So this is the deviation of light because of its original path because of a speed change. The index of refraction is a measure of how much light will bend. And it is the ratio of the speed of light in a vacuum to the speed of light in the medium. So index of refraction is the general speed of light divided by whatever the speed of light in the substance is. If you want to find the speed of light in the substance, you just divide the speed of light by the index of refraction. So what's the speed of light in a material with an index of refraction of 3? Well, the speed of light is 3 times 10 to the 8th meters per second, and is c over c medium. So a little bit of algebra gives us c medium is c over n. So 3 times 10 to the 8th meters per second divided by 3 gives us 1 times 10 to the 8th meters per second. If n is 3, the speed of light is 1/3 of what it is in a vacuum. And in general, everyday stuff has n in the low single digits. you're unlikely to see an end higher than 4. So at a certain critical angle, the angle of refraction is 90 degrees to the normal. And for any angle greater than incidence greater than that critical angle, you'll have total internal reflection, where the incoming light will be reflected inwards and nothing will leave. This will only happen when you're going from something with a higher index of refraction to something with a lower index of refraction. And this effect is how fiber optics work. That's how they keep light traveling down the fiber optic tube. And the index of refraction will also vary slightly according to the wavelength of light. So when visible light is refracted, the different wavelengths of light are bent at slightly different angles. Therefore, the visible light gets dispersed into a spectrum of colors. This is what's happening in a prism, making a rainbow. It's also part of what's happening in the formation of an actual rainbow, but the formation of an actual rainbow is a lot more complicated. Dispersion is happening, but the light you are seeing, the different colors are not all from the same raindrop. You're seeing different raindrops. But it does have to do with dispersion. Same effect, refraction, dispersing light into its full spectrum of colors. But you're seeing the interference pattern of millions of raindrops doing that. So, spherical mirrors. For a spherical mirror, the focal point is halfway between the center of the mirror and the center of the sphere that the mirror is from, the center of curvature, and the surface of the mirror. So the focal length is half the radius. So if a spherical mirror has a radius of 25 centimeters, what is its focal length? Well, that'll be half the radius. So 25 centimeters divided by 2, that's 12.5 centimeters. Images can be described in the following manner. An image can be real or virtual, it can be upright or inverted, and it can be larger or smaller than the object. And they're determined by several criteria, including the object's distance, the distance of the object from the vertex, the focal point of the spherical mirror, and the size and orientation of the object. So the distance of the image from the vertex is called the image distance, di. So if you have a concave spherical mirror and you have an object beyond the center of curvature, it will form a real, inverted, smaller image between the focal point and the center of curvature. If you have a concave mirror and you have an object that's located between the focal point and the center of curvature, it will form a real, inverted image that is larger and beyond the center of curvature. And if you have an object that's within the focal length of a concave mirror, it will form a larger, upright, virtual image on the far side of the mirror. And for a diverging mirror, a convex mirror, it will always form a smaller, upright virtual image. And to find the location of an image for a mirror, we can use the mirror formula, 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. F is the focal length. It's positive for concave mirrors. It's negative for convex mirrors. DO is the distance of the mirror to the object. DI is the distance to the mirror of the image. Negative distances are virtual images on the far side of the mirror. If an object is placed at a distance of 3 centimeters from a convex mirror of focal length minus 2 centimeters, where's the image? 1 over the focal length is 1 over the distance to the object plus 1 over the distance to the image. So minus 1/2 equals 1/3 plus DI. So DI ends up being minus 5/6. So 1 over DI is minus 5/6. So DI is minus 6/5 or minus 1.2 centimeters. The image is virtual, 1.2 centimeters behind the mirror. It'll be upright as well. Yes. Minus 1/2, minus 1/3. I subtracted 1/3 from both sides. Name? Okay. So lenses raised parallel to the principal axis will for a converging lens where it's parallel to the principal axis will converge at the focal point on the opposite side of the lens. And for a diverging lens, they will diverge from the focal point on the opposite side of the lens. For a converging lens, if the object is beyond the focal point, you'll get an inverted real image formed. For lenses, the positive DI is going to be, the real images will be on the far side of the lens, and they'll get larger as the focal length is approached. Inside the focal length, it forms a virtual image on the object side of the lens. And for a diverging lens, the image is always upright, smaller than the object, and on the object side of the lens, and virtual. So for the location of an image on lens, 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Focal length is positive for converging lenses and negative for diverging lenses. DO is the distance from the lens to the object. DI is the distance from the lens to the image. And negative image distances are virtual images on the near side of the lens. So the image location switches for lenses and mirrors. And yeah. So an object is placed at a distance of 20 centimeters from a converging lens of focal length 10 centimeters, where it is the image form. 1 over the focal length plus 1 over the distance to the object plus 1 over the distance to the image. So 1 over 10 equals 1 over 20 plus 1 over DI. So DI is 1 over 20. So DI is plus 20 centimeters. The image is real. 20 centimeters from the lens on the side opposite the object, and it will be inverted. Also, in general, virtual images are upright, real images are inverted. The human eye has a lens that focuses an image on the back of your eye, changes the focal length of the lens to focus on different objects. Your muscles can change the focal length. Glass is correct for weaknesses in the lens. So nearsighted glasses with diverging lenses, correct for nearsighted lenses, which is the ability to see objects clearly, nearby objects clearly, but not distant objects. The image forms in front of the retina. Diverging lens is correct for this. Farsightedness is the ability to see distant objects clearly, but not nearby objects. The image forms behind the retina. Glasses with converging lens correct for this common defect. This is also what happens when you get older and your eye muscle, your lens gets stiffer, and so it can't change its focal length as much. Polarization is the preferential orientation of the field vectors in light. Polarization of light can be attained by several means. The most common is the use of a polarizing or Polaroid film. That is not a polarizing film. That is a fraction rating. This is a polarizing film. This type of polarizer only allows the components of waves in a specific plane to pass. The human eye cannot detect polarization. So if you have 2 polarizers that are lined up, light will go in, half the light will get blocked by the first polarizer, and then the second polarizer will let it through. And if they're at right angles, the second polarizer will stop it. Diffraction is the bending of waves when moving past an opening or obstacle that has a size smaller than or equal to the wavelength. All waves show this type of bending as they go through relatively small slits or pass by the corners of objects. The larger the wavelength compared to the size of the opening or object, the bigger the diffraction. When 2 or more waves meet, they're said to interfere with each other. The resulting waveform is a combination of individual waves. You just add the waves up. The principle of superposition is the combined waveform is given by the sum of the individual waves. When interfering, it's possible for 2 waves to reinforce or cancel each other. So here is reinforcement. It's constructive interference. Here is canceling each other out. That's destructive interference. This is what active noise canceling does. You have active noise canceling headphones. They play a sound that destructively interferes with the outside noise. So important equations. Index of refraction is speed of light over speed of light in the medium. For a spherical mirror, the focal length is half the radius. The location of an image for a mirror is 1 over the focal length, 1 over the distance to the object, plus 1 over the distance to the image. Negative focal length is diverging mirror. Negative the eye is a virtual image. The location of an image for a lens Negative focal length is a diverging lens. One over focal length plus whatever DO plus whatever DI. Negative DI is a virtual image. Virtual images tend to be upright, real images tend to be inverted. And so now it is time for the quiz. I'm gonna share it here. We just need to use the right- So, let me know if you need it. You put away your phones. You get one sheet of note. Stop it.